So here's a quantum energy level practice problem. This is from practice midterm number 3. I think it is, summer session 2, 2020 midterm. Where was it? There we go. So we are taking a look at where was it? Energy levels given by this formula. So negative some constant value divided by n times 2n plus 1. And we want to know, based on that energy formula, we want to know what's the wavelength associated with the n equals 3 to n equals 4 transition. So in cases like this, I think it's a good idea to list out the possible energy levels. If we just plug in the first few n values, like if we just start writing out values for n, like let's say we plug in n equals 1. If you plug in n equals 1 here, what would this turn into? Yeah, we've got 1 times 2 times 1 plus 1, so 1 times 3. So we get negative E0 over 3. Then if we plug in 2 times 2 plus 1, so 2 times 5, it'll be negative E0 over 10. Then plug in 3 times 2 times 3 plus 1, 3 times 7 will be 21. Then plug in 4. So 4 times 8 plus 1, 4 times 9 would be 36. So we get these various values, all some fraction of negative E0. And as we are making the denominator larger, we're getting closer and closer to 0. So hypothetically, we could say that E sub infinity would be 0. But of course, we'll never actually get there. But we can list out these energy levels. It looks like these are getting closer and closer together. So let's say something like this. This is not necessarily to scale, but as a general idea, we could draw out a graph showing all these different energy levels. Make that a different color. There we go. So if we just show these energy levels on this sort of chart, these are the various permissible values for energy. The in-between values don't work. And we could keep this going up further, but it looks like for this problem, we only need to go up to 4. So we're going from state 3 to state 4. Is that an increase or decrease in energy? That is from negative E0 over 21 to negative E0 over 36. Is energy increasing or decreasing there? And how is that a decrease? How can we tell?
Would it be because the value on the bottom, like the denominator, is getting bigger, so therefore it's going to equal to a smaller value?
Yeah, we are increasing the denominator, which makes the result smaller. But keep in mind, these are negative numbers. If you make a negative number smaller and smaller magnitude, you're getting closer to 0 from below. So this is actually an increase in energy. The magnitude, the absolute value has gotten smaller, but we're talking about negative numbers. So this is an increase in energy. That increase is the delta energy of the system. As we go from 3 to 4, delta energy is, I guess we could just write that as final minus initial. So that'll be negative E0 over 36 as final, minus negative E0 over 21 as initial. And let's see what that's going to be. I guess we could factor out an E0. And we're left with positive 1/21st minus 1/36. So that'll be E0 times, do we have an easy common denominator there? That looks like it's going to take too long. So 1/21 minus 1/36. Yeah, that ends up being like 5 out of 252. So let's just put that as a decimal, round it off, about 0.0198. So that'll be the change in energy. And of course, the E0 is, in this case, 25 electron volts. So we know that to go from state 3 to state 4, the system has to gain this much energy. In other words, 0.0198 times 25 electron volts. And now how do we convert that into wavelength of a photon? How does the energy change of the system relate to the wavelength of the photon? Yeah, we can use the idea that the energy of the photon is h times c over the wavelength. And the energy of the photon is the delta energy of the system, at least absolute value of delta energy of the system, because the photon's energy should always be treated as a positive number. We know the delta energy of the system is this value here, so we can set that equal to hc over lambda, multiply both sides by lambda, divide both sides by energy of the photon, and that should give us the wavelength. And what's our usual value for h times c? Yeah, 1240 electron volt nanometers. We divide that by the energy, which was 0.0198 times 25 electron volts. Electron volts will cancel out, and we will be left with nanometers. So 1240 divided by 0.0198 times 25, I'm getting about 2,505. So that would be the wavelength of this light in nanometers, way beyond the visual spectrum, visible spectrum. Not sure what kind of light that's going to be, but longer wavelength means lower frequency and lower energy. Any questions on that? And then for part C, sorry, go ahead.
Why did we say that the energy increases going up the levels?
Yeah, we are going from a lower value to a higher value because 1/21st is smaller, or 1/21st is larger than 1/36th, but these are negative, so that reverses the order. Like for instance, 3 is smaller than 5, but -3 is greater than -5.
Oh, okay, yeah, thank you.
So we are, from the negative side, we're getting closer and closer and closer to 0. In fact, let me go ahead and mark 0 on this chart, because 0 is the hypothetical E sub infinity. So let's call this 0. And as we go to increased n values, we are getting closer and closer to 0 from below. So increasing n does involve increasing the energy here. And that's usually the way we set it up. We usually define these energy levels such that higher n value means higher energy and lower n value means lower energy. In order to gain energy, that energy has to come from somewhere. So that would be absorbing a photon in this case. In general, for the system to gain energy, you have to have a photon entering the system so that the system gains the energy carried by the photon. Emitting a photon would be if the system is losing energy, then that photon, the energy leaves in the form of a photon. You're welcome. Any other questions on that part? And then in part C, it's talking about the other element, sacramentium. which has a different value for E0. But this is one of the reasons I thought it would be a good idea to write out this chart in terms of E0 as an arbitrary constant. If we had used specifically the E0 value for Divisium when we calculated these, we'd have to calculate them all over again. But by writing it out in terms of E0, we should be able to use the same chart for both and just plug in the E0 value at the end. So let's take a look at starting in state n equals 3. So we're going to be starting at n equals 3 as our initial location. And this is asking, what are some different ways you could get from n equals 3 to the ground state? So if you're in n equals 3 state, how could you get to n equals 1 from there? Yeah, you're going to have to release energy, right? Releasing energy, let's say, drops you from 3 to 1, from initial to final. And that energy is going to leave as what? How does energy leave? Yeah, it's going to be leaving as 1 photon. So one way for this to go from n equals 3 to n equals 1, from this n equals 3 excited state down to the ground state, is by emitting a photon with exactly this much energy. And so we could calculate that in the same way. We could subtract final minus initial to find the difference. In this case, it's losing energy. So delta energy will be negative, but we would take the absolute value anyway. E photon is the absolute value of that change. So we want to figure out how much energy the photon is removing from the system. And then you could use hc over lambda to convert that energy to a wavelength again. And of course, the main difference would also be that you're using the 32 electron volts instead of 25. But largely the same procedure, just in the opposite direction. However, that's not the only way to get from 3 to 1. You could jump from n equals 3 all the way to n equals 1. Or how else could you get there? You could start in n equals 3 and then do what? Yeah, you could do this in 2 steps. It is entirely possible to start in the n equals 3 state and then take 2 steps, because you can stop at any legal energy state. You could go from 3 to 2 and stop there, and then also go from 2 to 1. So you could do that by emitting 2 photons. Emit 1 photon that has this much energy, find the wavelength associated with that, and then emit a second photon that has this much energy and find the wavelength associated with that. So these are 2 different ways you could go from n equals 3 to n equals 1. And there could presumably be more ways also. Maybe you could absorb a photon that takes you up to n equals 4 and then emit a photon that drops you all the way to n equals 1. But that wouldn't be just emitting photons. That would be absorbing a photon, then emitting 1 or more other photons. So I guess there's actually infinitely many ways, because you could go up to n equals 5 and then go back down to n equals 1, or go up to n equals 6 and then down to n equals 1, and so on. So there's infinitely many ways that this could happen. I assume C is not asking you for writing out infinitely many ways. But I think these 2 ways would be the main ones involving losing energy. And then maybe you might also mention that it could absorb a photon to go up to a higher energy state and then emit 1 or more to go back down to n equals 1. Any other questions on that so far? Or any other questions on the energy level stuff in general? All right, then let's take a look at the previous example on Doppler effect, because there's been several questions about that as well. That was the submarine one up here. So in this case, this one's kind of weird because we don't have just one object. I mean, we got one object emitting sound, but then that sound echoes off of another object. So we have 2 submarines. let's say submarine 1, let's say your submarine, and somebody else's submarine. And the idea is your submarine is emitting these radar waves, so a wave of light at a frequency of 40,000 hertz, 40 kilohertz. And you get back frequency 39,998 hertz. So let's try setting up some labels here. Let's say you send out a ray of light, a radar wave, with a frequency of 40,000 hertz. I'm going to call that F1. And you eventually receive back a ray of light with a different frequency. But what did that ray of light have to do in order to get back to your location? This ray of light is traveling from your submarine, and then it does what? Does it just keep going forever? Yeah, it's going to reflect back. It bounces off of the other submarine. And in so doing, it's going to change. So we're going to have to take into account the ray of light hitting the other submarine. And the other submarine is actually going to detect this as a different frequency. Because why would the frequency produced by your submarine and the frequency absorbed or observed by the other submarine be different? What's going to cause a difference in frequency there? Yeah, the other submarine is moving. And it doesn't tell us how fast it's moving. I don't think it tells us which way it's moving either. Does it tell us which direction it's moving? So I think we can just say the other submarine is moving, but we don't know how. Or does it say it's moving away? Let me find that. Oh yeah, it does say an object moving away from you. So we do know that the other submarine is moving away. So we may as well mark that. We know that it is moving away. So this is the velocity of the other submarine. But we don't know how fast it's moving, of course. So the Doppler effect is going to mean that the frequency observed by the other submarine would be different. But that other submarine reflects that sound back. Sorry, not that sound, that light. These are radio waves, not sound waves. So the radio wave is going to reflect back at that same frequency, the same F2. We just don't know what that is yet. And is that F2 the frequency you're going to observe when it bounces back? No, that's going to be different also, right? Because in this case, for the return trip, this is a radio wave that has bounced off the other submarine. So we're going to treat other submarine as the source, and then your submarine is the observer. So we're going to get a third frequency, let's call that F3, which we know is 39,998. So we know the frequency that you produced. We don't know the frequency the other submarine receives and reflects back, but we know the final frequency that that turns into when you pick it up again. And we want to use that to figure out how fast how fast the other submarine is moving, and also what frequency that other submarine would be observing. Because we can do this using the Doppler effect. We're just going to need to apply the Doppler effect formula twice, because we really have two Doppler effects. The Doppler effect for the light on its way from your submarine to the other submarine, and then Doppler shifted again on the way back. So let's try setting up an equation for each one of those. And what is our usual Doppler effect equation that we can use here? F observed equals what?
Would it be the wave speed plus or minus the speed of the observer?
Yeah. Is that the numerator?
Yeah. And then on the bottom, it would be the speed of the wave plus or minus the speed of the source, then multiplied by the frequency source.
Yeah. So the speed of the wave plus or minus speed of the observer, and the speed of the wave plus or minus speed of the source. Like this. And I'm going to make two copies of that because we have one for the outbound journey and one for the inbound journey. So let's try filling in as much of each of those as we can. For the outbound trip, which one of these frequencies would be the observer frequency? Yeah, F2 would be the observed frequency, and F1 would be the source frequency, because that's the frequency you're creating. And then V is going to be speed of light in water, which is given. That's the 2.25 times 10 to the 8th. I'm just going to leave that as V for now. We can fill it in later if we need to. And then V observer, we don't know. That's the speed of the other sub. But V source, you're not moving, so that's just going to be 0. And how would we decide whether to use plus or minus here? If the other sub is moving away from you, what would you expect to happen to the frequency? Yeah, if the other sub is moving away from you, that means the waves are going to be more spread out from the other submarine's perspective. It's going to take more time for each extra wave front to catch up. So that means we should expect a lower frequency. And in the numerator, we would want a lower value to create a lower result. And then plus or minus 0 is still just 0. So we end up with F2, the frequency observed and reflected by the other submarine, is F1, the frequency you created, times this ratio. Speed of light in water minus speed of the other submarine divided by speed of light in water. And then for the return trip, let's try the same setup. But in this case, the wave is bouncing off of the other submarine. So we're going to treat F2 as the source. Why are we treating other submarine as the observer? In this case, as the ray of light, as the radio wave goes from your submarine towards the other submarine, your submarine is creating the wave, so you're the source. The other submarine is receiving that wave, so it's the observer. But then when that wave bounces off, we would treat the wave that has just bounced off the other submarine as the source, and then you're receiving it as the observer. So in the return trip, F2 is the source frequency and F3 is the observer frequency. And now the observer, your submarine, is going at speed 0, but the source is the other submarine, so that'll be speed of the other submarine. Yeah, if you just have a wave that's bouncing off of something, the frequency does not change as a result of the bounce. The only thing that changes is the direction. It's changing from going in one direction to going the other direction. And also a wave bouncing off of something can change its phase. There may be a delta phase shift involved. Typically either a phase shift of an extra plus pi half a cycle or a phase shift difference of no difference at all. Depending on how exactly it reflects, I think it's depending on whether it's going from slow and bouncing off fast or from fast and bouncing off slow. But it's possible that the bouncing off causes crest to turn into trough and trough to turn into crest. But that doesn't influence the frequency at all. So frequency is going to stay the same during the bounce back. In fact, even a wavelength is not going to change because it's still in the same medium. But we do have a change in direction. And then as it encounters something in another reference frame, something going at a different speed, that thing at a different speed will perceive a different frequency. So that's the Doppler shift here. Speed plus or minus 0 is still just speed of light, so we don't have to worry about that. As for the other one, would the source moving away from the observer lead to higher or lower frequency overall? Yeah, it should be lower. If the source is moving away from you, then the wave fronts are going to get more spread out in space. Yeah, we should have an addition here because addition leads to a larger denominator, which results in a smaller final result. And that's what we should expect. So we've got two Doppler shift equations. Any questions on that so far? And now here's the mathematical magic. We know that F2 equals this formula. What can we now do with that formula? Yeah, we can plug this into the other one. Yeah, you can treat this as a system of equations because we know F1, we know F3, we know speed of sound in the material or light in the material. We only have two unknowns, V other submarine and F2. So you can treat this as a system of two equations, two unknowns, and it's not linear. So the usual elimination method doesn't work, but substitution definitely works. Everywhere you see F2 in the other equation, you can just replace that F2 with this formula, F1 times V minus V other over V. So let's try that. If we combine these together, we get F3, just copying out the return trip equation, equals, and then replacing F2 with the formula we have for F2. F2 is F1 times this fraction V minus V other over V. And then the other fraction is just the same V over V plus V other. So we now have a new equation that involves only one unknown, right? Because we know F1, we know F3, those are given. We know speed of light in the material, that's given. The only unknown left is V other. Also, we can simplify this a bit. As we combine these into one fraction, we've got a times V in the numerator and a times V in the denominator that'll just cancel out. So we're left with F3 equals F1 times V minus V other over V plus V other. Any questions on that so far? So let's tidy that up a little bit. We've got F3 equals F1 times V minus V other over V plus V other. And we want to ultimately solve for speed of the other submarine. Problem is that shows up in the numerator and denominator here. Is there any way we could address that? Any way we could make it so that it only shows up in the numerator or only in the denominator? How would you just get rid of the denominator here? Yeah, I would multiply both sides by that entire denominator. Multiply both sides of the equation by V plus V other. So that'll give us F3 times V plus V other equals F1 times V minus V other. That at least gets it, the variable we're trying to find out of the denominator. if we then distribute, we now have the only problem being that v other, the variable we're trying to find, shows up on both sides of the equation. But we can deal with that by just moving all those terms to one side of the equation. So let's say we add f1 v other to both sides. And let's say subtract f3v from both sides. Now we've got all the terms with the variable we seek on one side of the equation and everything without that variable on the other side. And since v other shows up in both of these terms, what can we do with that? Yeah, combine those together. Essentially, we are factoring out v other, left with just f1 plus f3. In fact, we could even factor out speed of light from both of these terms and get speed of light times f1 minus f3. And then what's the last thing we need to do to solve for v other? Yeah, divide by f1 plus f3. So speed of the other submarine is speed of light times this ratio of the difference in frequencies divided by the sum of the frequencies. And we can now do that. We can plug in those values. We got, for instance, f1 minus f3. f1 minus f3 would just be 2 hertz. Because if you subtract these, 40,000 minus 39,998, that's just 2 hertz. And then if you add them, 40,000 plus 39,998 would be 79,998. Hertz and hertz cancel out, so we get 2 over 79,998, which is 39,999. So we end up with the other submarine is going 1/39,999th of the speed of light. And we have the speed of light, 2.25 times 10 to the 8th. So if we plug that in, 2.25 times 10 to the 8th divided by 39,999 is about 5,625. Which would be in meters per second, which is kind of nonsensical because that's an object traveling underwater at 5.5 kilometers every second. So this is not a very realistic problem. I mean, I wouldn't expect to see something going that fast in air unless it's like a supersonic jet, let alone underwater. But that's what we get from the numbers given. Any questions on that so far? And now that we have that, we can also find F2 by just plugging this value in for V other in this equation for F2. So F1, 40,000 times speed of sound or speed of light in water minus 5,625 divided by speed of light in water. And that result will tell you the frequency observed by the other submarine, which I'm guessing should be close to 39,999. Not exactly that much, but probably pretty close to it. Any other questions on that?
Yeah, really quick. Why is the F2, the arrow pointing to the other submarine, why is that? Why are they the same F2?
Because it's the light that reaches the other submarine and the light that bounces off the other submarine. The bouncing off process, the reflection, doesn't change the frequency. Like for instance, if you shine a certain color of light on a mirror, the same color of light should bounce off. The bouncing off process shouldn't change the wavelength and frequency.
Okay, thank you.
Mm-hmm. And as for why it says you can't get a numerical answer in part A was basically just setting up this system of equations. So you can get a numerical answer, but only by going through the whole process we just did of solving for the whole thing. So I guess it's more, you can't get a numerical answer yet, but by solving the system of equations, you do. Any other questions on that? Or any other problems from this you'd like to work on? Yeah, let me pull up that file you sent me for the multiple lenses thing. Where did that go? There it is. Is this the one? Okay, so we have two lenses, lens 1, lens 2. We don't know the focal lengths. Excuse me. But we are told that if we place the lenses in this sort of arrangement, 20 centimeters apart, and we have a 5 centimeter object 30 centimeters before the first lens, the final image is going to be this virtual image here. So this is the final image created by both lenses together. So we're going to have to sort of reverse engineer that process. So let's try this one step at a time. First of all, we've got this object. So ignoring lens 2 entirely for the moment. We've got an object, we've got lens 1. Lens 1 is going to create some image. So let's say we've got an object, and we know the object distance at least. Let's call this object 1. Object distance 1 equals 30 centimeters. We don't know the focal length. In fact, we don't even know what type of lens this is. Might be real, might be converging, might be diverging. So we don't even know if f1 is positive or negative. But we do know object 1 is 30 centimeters. And we know that's going to create an image, but we don't even know where the image is. Might be a real image, might be a virtual image. Let's assume for the moment that it creates a real image. Presumably, we're going to do some sort of ray tracing. That doesn't look good. Some sort of ray tracing. Maybe we've got, and I'm just eyeballing the ray tracing here. I have no idea where the focal length actually is. But maybe we do some ray tracing and we come up with something like, that's not even accurate. Let's say something like this. Close enough. Let's say we do the ray tracing and we come up with an image like this. So there's our image. So if that's the image from the first lens, so that would be distance I1. What's the next thing that happens to that light? Does the light just stop there? Does the light hit somebody's eyes? Where does that light go next? Yeah, it's going to travel to lens 2. First, we actually don't know that the first image is real. We don't know whether the first image is real or virtual. I'm just saying, suppose it's a real image for purposes of this ray tracing. If it ends up being a virtual image, we'll get the same result, except that I1 will be a negative value. But in general, if some value could be positive or negative, and you're just trying to set up an arbitrary general description, usually I would go with the case where that value happens to be positive and try working it out from there. And then if it turns out it's a negative number, you'll just plug a negative number into whatever formula you get. So I'm treating this as assume it's a real image for now, because that would lead to I1 being a positive value. And I think that's going to make the equation easier to set up. But yeah, we know that what's going to happen next is these rays of light hit lens 2. And for purposes of lens 2, we can now ignore everything that happened before this and treat the image from lens 1 as if it's the new object for lens 2. This is really the key to any multiple lens or multiple mirror setup. The first mirror or lens turns the original object, the actual physical object, into an image. That image from the first lens or mirror acts like the new object for the second lens or mirror, because the image is where the final rays of light seem to be coming from, and where the rays of light come from is effectively the object. So as far as lens 2 cares, this is the object. And how would we write out the new object distance, the distance from that fictional object to lens 2? Because that's what we're going to call O2. How are I1 and O2 related to each other? Yeah, they should add up to 20, right? In general, the image distance from the first lens plus the object distance from the second lens should equal the distance between lenses. In general, I1 plus O2 should equal D, the distance between lenses. And it turns out this actually even works if you are using a virtual image. If you're using a virtual image, it'll be back here, but I1 will be a negative number. So the equation still works. So O2 is going to be distance between lenses minus image distance 1. And again, because of the way the positives and negatives are set up, this will work even if I1 is negative. So in this case, 20 centimeters minus I1. And now we're getting somewhere, because for lens 2, if we set up the same sort of analysis, F2 is still unknown, but we know O2 is 20 centimeters minus I1. Again, we don't know what I1 is, but we can at least write it in terms of that unknown. And I2, the actual image distance, is 4 centimeters. However, since it's a virtual image, that'll be -4. So we have some values. We can chain those values together in terms of the thin lens equations. For example, we know that 1 over F1 equals 1 over O1, which is 30, plus 1 over I1. Likewise, we know that 1 over F2, which is unknown, equals 1 over O2, which is 20 minus I1, plus 1 over I2, which is -4. So that becomes -1 over 4. So we have several unknowns here. It looks like our unknowns are, we don't know F1 or I1 or F2. So we've got 3 unknowns, but only 2 equations. If you've got 3 unknowns, how many equations should you want to have? Yeah, we want as many equations as we have unknowns. We're going to need a 3rd equation. So we do need one more piece of information. But it looks like we also know the final height here. We know that the the final image is 2 centimeters tall. So that would be the final image height. We could use that to figure out the magnification. The magnification, the total magnification is -2/5, because the final image is -2/5 as tall as the object, with the negative because it's upside down. And that -2/5 should equal the total magnification. We actually don't know whether lens 2 is converging or diverging yet. We're going to have to figure that out by figuring out the sign of F2. So we don't know anything about either one of these lenses. We do know that the total magnification is -2/5, because the final image is 2/5 as tall as the object and upside down. How does total magnification relate to the individual magnification from each lens? Yeah, that should be M1 times M2. And each one of those M's could be written as -I over O as usual. So we could write that as -I1 over O1 times -I2 over O2. And now we've got another equation we can use. We can cancel out the negatives, and we end up with negative 2/5 equals I1 times I2 over O1 times O2, combining those fractions together. And I think we know some of those. We know O1 is 30. We know I2 is negative 4. And we know O2 can be written as 20 minus I1. So that's now an equation that relates I2 and I1. Wait, I2 was, sorry, that was, I1 is unknown. Let me fill that back in. I1 is unknown, but we know I2 is negative 4. So we now have a third equation. In fact, this equation could actually be solved for I1 because I1 is the only unknown left in this. So you can solve this in the same sort of way. Multiply both sides by the denominator. And just like we did for the Doppler equation, move all the terms with the unknown variable I1 to one side, all the terms without it to the other side, factor and divide. And you'll end up with I1 equals some number. I2 is a negative number though. So I2 is negative 4 centimeters. The negatives that are already here cancel out because we've got a negative here and a negative here. So those just cancel out. So M total is just I1 times I2 over O1 times O2. So solve that for I1, and then you can plug I1 into both of these equations. And I think that should just be solvable for F1 and F2 individually, because at that point, each one of those equations has only one unknown left. So I think that should be the final piece of the puzzle for solving for the image distance one using magnification, and then use that to solve for each focal length individually. Any other questions on that one? All right, feel free to email me if you have any other questions, and I will see you next time. You're welcome.